In this series of videos, we're going to be reviewing the naming system for the two main categories of inorganic acids, the first of which and simplest of the two varieties are what we call the binary acids, so named because they only contain two different compounds. Before we actually get to reviewing the naming system, though, we should probably remember what an acid actually is, that being any compound that loses a positively charged hydrogen ion whenever that compound is added into water. So for example, HCl, probably the most well-known binary acid, loses this hydrogen, which becomes a positively charged hydrogen ion when it is added to water. By definition, this means that acids exclusively exist within the aqueous state of matter. So for example, this acid here technically would not be an acid, and in fact, if we name it hydrogen chloride, or technically hydrogen monochloride, if we follow standard covalent nomenclature systems, hydrogen chloride is actually the correct name of this acid when this molecule exists as a gas, but when this compound is actually dissolved in water, only when it is in its aqueous form do we consider this compound to be an acid, in which case, because HCl only contains two elements, the first of which being hydrogen, because every acid requires a hydrogen to lose, and we can see that the other element within its formula is some sort of other non-metal, and in the case of HCl, as well as most of the most common binary acids, this non-metal is usually going to be a halogen. So, for example, HF, HBr, and HI are all of the acids that contain a halogen as the second element, and all of these would be considered binary acids as long as each of them is dissolved and allowed to react in water. So now that that's out of the way, we can look at HCl as an example to demonstrate the naming system. And the first thing that we can do is we can name the non-metal. So for Cl, this is obviously going to be chlorine, and this forms the root of our acid name. Secondly, we add the prefix hydro to the name of the non-metal to indicate that this is a binary acid. We should probably write that there. And we indicate that this is a binary acid because hydrogen is one of only two elements that exist within this compound, the other one being the non-metal that is at the root of this name. And likewise, if chlorine were in an ionic compound, we are going to remove the suffix -ine from the name here, only instead of replacing it with IDE to show that this is an ionic compound, we're going to replace this with the suffix ic acid in order to indicate that this is indeed dissolved in water and therefore is behaving as an acid. So the name of our compound would be hydrochloric acid, and the most famous example of how hydrochloric acid is used is actually in your stomach to help you digest food. Although, as we can see in these pictures here, HCl in particular has a much more nefarious history, which brings us to our discussion of where binary acids actually come from. So most binary acids can be directly produced in a relatively simple synthesis reaction that is done between the non-metal and hydrogen gas. So if we were to take hydrogen gas, which we write as H2 because it's diatomic, and if we react this with chlorine gas, here Cl2, again in its diatomic form, the two elements would react together and undergo a very violent synthesis reaction. This reaction releases a lot of energy because both hydrogen and chlorine are very, very unstable gases, and then we would get, at least in the initial form, we would get hydrogen chloride, which is the gas form of this molecule. But once again, if we were to actually dissolve this in water, we would then get, in the aqueous form, hydrochloric acid. Now, as mentioned, this is the most straightforward way to produce all binary acids, and you could pretty much substitute any halogen in here, and the reaction would work identically. However, there is a much more disturbing history involving chlorine gas specifically because halogens or halogen gases, especially chlorine gas, have historically been used as chemical weapons, the first of which or the first documented instance of chlorine gas being used as a chemical weapon was here in World War I. And anyone who has studied World War I history knows that the Battle of Ypres, which is one of the major battles in Belgium during the First World War, was the first documented instance of chlorine gas being deployed on the battlefield, where it actually undergoes this reaction here. So chlorine gas is particularly deadly because of its ability to react with water. Now, why is this a big deal? Well, if you consider that 70% of the human body is made of water, this makes chlorine gas very, very deadly because it can literally react with what your body is mostly made of. And at this point, we actually get two different acids that are formed, and because chlorine is reacting with water directly, the HCl that is produced dissolves in water immediately and can therefore act as an acid. And in addition to this, we also get a second acid, which is what we call hypochlorous acid, the name we'll get to in a future video. But the point is that both of these acids are produced inside of your lungs when you actually inhale chlorine gas, meaning that these acids are produced and dissolve in the water in your lungs and proceed to melt you, or specifically melt your lungs from the inside out, and you end up drowning in a combination of your own blood and your liquefied lungs, which is why soldiers in World War I who breathed in chlorine gas would describe this feeling of having their lungs on fire and simultaneously not being able to breathe. And supposedly this is one of the most horrifyingly painful ways to die. So naturally there were instances, particularly of the Imperial Japanese Army using chlorine gas in World War II, despite the fact that chlorine gases and any halogen gases were labeled as weapons of mass destruction by the Geneva Convention after World War I and remain illegal to this day for reasons that I think are self-evidently obvious. On a less dark tone, you can take a look at the practice problems below to make sure that you have a handle on how to name and write the formula for each of the different binary acids and identifying the synthesis reactions used to make the acid forms of each of the binary acids below.